So again, this is what we had before. We have the Faulkner scan solution, and let's call it general thin layer Navier-Stokes. We define the grid, that still works, and let's still set our initial gas as a parabola. And in the Newton situation, so let's first do a little bit of let's first try to specialize this to a case where C is equal to 0, right? At the beginning, we need the initial condition, right? So when C is equal to 0, this whole memory term is 0. We don't have, it's the beginning of the boundary layer. So the only thing we have to modify is we have to put in this alpha prime. So let's still use the same A to denote our alpha prime. It's just that these two numbers has to change. The weight of these two terms has to change in our equation. So let's go to our equation, and we want to open the G. Okay, and it's GA that codifies the equation itself, right? So let's change GA. That's the only thing we need to change. The definition of FP, FPP never changed. They are just the second and first derivative of F. The boundary condition we already said is the same. So on this, we need to change the Fs term. This is the Fs term. It's still multiplied by A. But this term is multiplied by 1 plus A divided by 2. So let's change that. 1 plus A, now we need to divide by 2. That's the only change we are making. Alright. Okay, let's copy the divide by 2 and also go to the Jacobian. Every time we change equation, we need to change the Jacobian. So we have to divide by 2 here, divide by 2 here. So this is the terms of the Faulkner scan. No, this is the term relating to the F times FPP, right? Okay, now let's solve it and look at what it gives me. Something is wrong. Okay. Oh, we haven't run this yet. So we want to define the grid, initial gas, and Newton's iteration. Let me see if it converged. Yeah, it converged very nicely. Alright, so we get an initial condition that corresponds to a stagnation point flow. Alright. Okay, now let's start looking into how do we codify the right hand side. So for the right hand side, we need to pass in some additional information. First, we need to pass in what is my U at the previous I point or the previous C point, right? And to pass in both U and F. So why don't I just pass in the entire solution vector at the previous step? That's what we are going to do. So we are going to pass in, so instead of Newton's relation, we say, okay, advance in eta. So let's for eta is equal to 0 to, let's use a d, that's C, not eta. So advancing C, sorry, dx, let's solve it to 10, right? And let's set a dx. Somebody tell me what kind of dx should I use?
0.1.
Huh?
0.1.
0.1. Okay, sure. So when I do this, I need to compute my A now, right? And what is my A? In the beginning, so let's say what is my A? My A is defined as my A is defined as C over UE times dUE dx, right? And somebody just give me an example analytical UE as a function of C. That let's start with 0, right? Starting from a stagnation point and goes to some constant. Let's try something like that. Okay, let's try something that is UE C starts with 0 and goes to some constant. Let's say just 1. All right. What kind of can you just give me an example function to use? Square root of zeta. Okay, let's try that. Okay. Wait, is that actually gonna give me a Faulkner-Skein solution? I think so, right? That's actually going to, huh? It's a power law, right? Let's choose something else. Exponential? Good idea. Let's try something. Okay, is equal to, so let's set an exponential that converges to 1, right? So it's 1 minus e to the, what? Minus c. Okay, good. So let's just try that. So if I have this, then my due dc is going to be it's just going to be e to the minus c, right?
Yeah.
Okay, so then my alpha prime is going to be c over ue times e to the minus c. So what I get is c times e to the minus c, 1 minus e to the minus c. Okay, let's do that. So my a is going to be equal to c times e to the minus c divided by 1 minus x to the minus c. Except for when c is equal to 0, this is going to get me a 0 divided by 0, right? But we can always take the limit. So, okay, so e to the minus c is going to give me 1. Okay, so this is basically c divided by this. The slope is basically 1 at the beginning, right? So basically at the limit, if you take the limit of c goes to 0, is equal to what? I mean, this thing is going to be 1. You have c divided by this function as c approaches 0. One, right? I mean, 1 minus. I mean, you basically need to do a Taylor series expansion of 1 minus e to the c, and the ratio is going to be 1. So if is equal to 0, then a is equal to 1. So that's a special case we have to do to avoid the 0 divided by 0. Maybe we can avoid this somehow, but I don't know for sure.
Should the if condition be on top?
Then it's gonna be overwritten, so we can either do this or we can do else, right? Can do else. A is equal to that. Either way, it's gonna be fine. Okay. This makes you happier?
No. I thought z. So before a was defined first, so I thought the first iteration a could be.
Yeah, a is gonna produce not a number.
Right.
So doing this way, I think it'll avoid a complaint by MATLAB.
Right.
All right. So that's good.